Hi everyone, today we're going to finish up chapter 5. We're going to start by talking about something that is optically active or a chiral molecule without a stereocenter. So remember, stereocenter just means that we have a carbon atom that is attached to 4 different substituents. So there's 2 different types of cases that we're going to look at. The first case that we're going to talk about is something that is conformationally restricted. So what this really means is that it's going to be locked into a chiral conformation due to too much steric strain with the molecule. Another example that we'll look at is going to be something that is called a 1,3 disubstituted allene. And what an allene is an atom that has a double bond with each of its adjacent carbon atoms. So again, it's really important to get used to the terminology for all of these types of molecules and functional groups that we have talked about throughout the semester. So let's look at the first example. So the first example is going to be restricted rotation. So if we look at this molecule right here, so we have sp2 hybridization, so we would expect the molecule to be planar. But the problem that we experience is that when we're looking at this molecule, this is going to be too sterically hindered. So a quick refresher, if we think about tert-butyl, so we talked about this when we were doing naming. So a tert-butyl group is pretty bulky. So we have a carbon attached to our ring in this case right here, and then we have 3 CH3 groups coming off of it. So there's a lot of steric strain associated or steric hindrance associated with this molecule. So what actually happens is if we look at enantiomer A, so looking right here, we can see that this ring on the left is actually going to tilt out. So this bold part right here is indicating that it's a wedge, right? So it's going to be tilted towards us. So this is one possible molecule that can form, so enantiomer A. If we draw the mirror image of this molecule, we can look over here to enantiomer B. So in this case, the right-hand side ring is going to be tilted out towards us, again indicated by that dark wedge. So the molecule is going to be locked into one of the 2 chiral staggered conformations. So again, it has to be locked into one of these conformations just due to all of the steric hindrance associated with this molecule here. So another example that we're going to look at is going to be the 1,3 disubstituted allene. So when we're looking at the disubstituted allene, again, we have a chiral center without a stereocenter. So let's look at this molecule here. So when you're thinking about these 1,3 disubstituted allenes, it's really important to think about how pi bonds have to orient to be able to form that pi bond. So when we draw the enantiomer of this molecule, I'm going to label these carbons because I'm going to talk about them a little bit. So again, we have no stereocenters here. So none of these carbon atoms are attached to 4 different atoms, so we can say that there's no stereocenter or no asymmetric carbon atom. If we look at carbon 1 and carbon 3, so these are sp2 hybridized. So we would know that they would be planar. When we think about their planes are going to be perpendicular to each other. And the pi bonds are going to be oriented 90 degrees to each other. So that's what's causing, if we're looking here at this hydrogen and this chlorine here, it's causing that hydrogen to be pointing out towards us and that chlorine to be pointing into the page. So an allene is chiral if each end, so the ends are going to be this carbon and this carbon, has 2 different substituents attached to it. So in this case, we have a hydrogen and a chlorine. So let's talk about some optically inactive compounds and mixtures. So what does it mean to be optically inactive? So if a solution is optically inactive, it means that it does not rotate plane polarized light. So think of the cases where you can imagine that something would be optically inactive. So if we have a molecule that is achiral, so remember, a molecule that is achiral, what that means is that we just have identical mirror images. Another possibility, which we mentioned a little bit in the last lecture, is that the solution contains chiral. So again, something that's chiral would be optically active or would rotate plane polarized light. So the solution would contain a chiral or optically active molecule that cancels out each other's optical activity. So thinking about this, again, we mentioned this last time, we mentioned racemic mixtures. So a racemic mixture, just a quick refresher. A racemic mixture is when we have our enantiomers in a 1-to-1 ratio, so equal amounts of both enantiomers. So racemic mixtures are not optically active because their rotational effect of one enantiomer is canceled out by the other enantiomer. So let's talk about briefly D-carvone and L-carvone. So D-carvone, sorry, I have no idea what that is. So D-carvone was our positive carvone, right? Because it's going to rotate the plane polarized light in a clockwise direction. We have L-carvone, which again, L-carvone is going to be rotating the plane polarized light in a counterclockwise or negative direction. So it's shown as minus carvone. So if we have something that is racemic of the D-carvone and the L-carvone, how it's represented is going to be like this, plus, minus, carvone. So showing it like this indicates it's a racemic mixture. Again, racemic mixture just means that we have equal amounts of both of those enantiomers. If we have equal amounts of both of those enantiomers, that would mean that this would not be optically active. Again, it wouldn't be optically active because the rotation of the positive is going to cancel out the rotation of the negative direction. Next, we're going to talk about mesocompounds. So mesocompounds are compounds that are achiral. Again, achiral is going to indicate that they're optically inactive, but they contain chiral centers. So let's look at an example. So let's look at 2,3-dichlorobutane. So when we're looking at 2,3-dichlorobutane, let's think about all the isomers that we can draw, and let's think about what we would be optically active. So we can draw, so this is where, again, stereochemistry is really starting to come into play when we're thinking about all of the different isomers that we can draw. So again, we want to always label our stereo centers as R and S. This will be really good practice. You guys can go through of these. So again, remember you can write the R and S right at the stereo center. That's the most standard way that these are drawn. So here are our 4 isomers that are possible to form. So when we look at these 2 molecules right here, versus these two molecules here. So we'll call this A, B, C, D. So looking at A and D, these are going to be enantiomers to each other. Right, so we have RR configuration and SS configuration, which again, when we're switching the configuration from R to S, that indicates that they are enantiomers to each other. So when we have an enantiomer, if no matter how many stereocenters that you have, all those stereocenters have to flip to be an enantiomer. So again, those A and D would be considered enantiomers. When we're looking at B and C, so B and C are actually going to be the same molecule. So if we think about bond rotation, again, we can rotate amongst a bond if it is a single bond, right? So we don't have a lot of strain associated with it or energy needed to break that or to rotate that bond. So when we rotate the bond, what's going to happen is we're going to have something that looks like this. So this would be B, and something that looks like this, which would be C. So just imagine rotating right amongst here, right amongst here. So if you look at these two molecules, we can see that we have an internal mirror plane, right? So the two similar halves of the molecule have the same configuration, right? So again, imagine an internal mirror plane. So these compounds here would be considered meso compounds. So looking at the isomers of 2,3-dichlorobutane, we can say that we have 3 unique types of structures. So again, the most important thing for these, I think, is to just draw the configuration, so the R and S configurations. And if you have something that's an enantiomer, if it was R in one of the compounds, it needs to be S in the other compound. And that's the case for all stereocenters. So the next thing we're going to talk about is going to be Fischer projections. So Fischer projections are really important in something like biochemistry. And if you guys go on to take Organic 2, you will talk about them when you talk about carbohydrates. So that it is a really important topic. I'm just going to go through it really briefly. So Professor Rosenstein and Professor Madrick, we decided not to put this also on quiz 5. Again, this will be covered in depth in biochemistry. And if you guys have time in Orgo 2, you will briefly talk about it with carbohydrates. So what Fischer projections really are, again, they're used a lot in biochemistry. And what it is a quick and easy comparison for chiral compounds. So Fischer projections are always drawn as a cross with vertical bonds going back and horizontal bonds going forward. So let's look at lactic acid. So if we draw the standard view, which all of you are used to now, we have something that looks like this. So we'll call this our standard view. So what this is going to be equal to if we're writing the Fischer projection. So imagine pulling this methyl group towards pulling it down in this direction, and you think about flattening the OH and the hydrogen. So again, the OH and hydrogen, the wedge and the dash are always going to be our horizontal bonds, and then our CO2H right here and our methyl are going to be our vertical bonds. So it's going to look like this. So these are going to be going back, and then our alcohol and our hydrogen are going to be coming towards us. So this isn't really a common way to write the Fischer projection. How it is drawn is going to look like this. So the point right here, this represents a stereocenter. And again, anything that was wedged or dashed is going to be on the horizontal. So our alcohol and our hydrogen are going to be on our horizontal. Horizontal indicates that it is going forward, where anything that is vertical indicates that it's going back. And again, this is going to be talked about in detail when you take biochemistry, and you will talk about it hopefully next semester if we have enough time in 255. So again, you won't be quizzed on this with Chapter 5 quiz. So the last part that we're going to talk about is we're going to talk about stereochemistry in chemical reactions. So for this part, don't feel overwhelmed if you don't know the mechanisms behind the reaction. So this is really just showing you that many of life's molecules are chiral. So if we think about like proteins, hormones, drugs, etc. And the major goal of organic chemistry is to create molecules that are going to be chiral. So this field, the study of kind of forming chiral compounds, is referred to as asymmetric synthesis, which makes sense, right? So if it has a stereocenter, it's going to be typically a chiral molecule, which we would say it's an asymmetric carbon atom. So there's a couple different terms that we want to be familiar with. So we have stereospecific and we have stereoselective. So when we're talking about stereospecific, the reaction only produces one possible stereoisomer. So this is not as common, right? It's not as easy for this to happen. Stereoselective is when the reaction will yield one possible stereoisomer in excess. So when we're looking at different examples, so example 1 and 2 actually are going to be all of chapter 6. So again, don't feel overwhelmed by not understanding the reaction that's taking place. We're going to go into a lot of detail with this. So example 1 is just showing us direct displacement. So these are going to be known as SN2 reactions. So these are substitution reactions. So this reaction here is going to be stereospecific, which again, that means that we're only producing one possible stereoisomer. So if we have iodide and we have this molecule here, what happens is this chlorine is going to be our leaving group. So chlorine is leaving and the iodide is going to come in and attack. So we're going to have a compound that looks like this. So again, this chlorine's leaving, the iodide's coming in and attacking that carbon. So this product here is considered an inversion product. And again, this is stereospecific, so we have one possible product formed. Another example that we are going to look at, so we have SN1 reactions. So SN1 reactions is when we're looking at dissociation and addition. So this means that we're going to have both an inversion and a retention product, and these are going to be racemic mixtures. So if we look at this molecule here, again, this is just showing you how stereochemistry plays into everyday chemistry. We will go through all of these mechanisms in the next chapter. So again, chlorine is going to be our leaving group. We're going to form this intermediate carbocation. So again, this would be planar. And what's going to happen is our iodide is going to come in here and attack that carbocation. So we can have two different types of attacks. We can have an attack from the back and an attack from the front. So again, remember that this carbocation is planar, which allows us to have that attack from the front or the back. So this is where those two different products are coming into play, the inversion and the retention product. So inversion just means we're inverting the stereochemistry. So again, this would be our inversion product. And then if we think about the attack from the front, so the attack from the front is going to be called our retention product. So the iodide is really just replacing the position that this chlorine is in when we have retention. So again, this would be considered our retention product. So these are enantiomers, and they will be a racemic mixture. So we will have a 1-to-1 ratio of both of those enantiomers. So again, 1-to-1 ratio would mean that it would be optically inactive. So let's look at some reactions generating a new chiral center. So if we have this molecule here, we react it with H2 and a nickel catalyst. What we are going to form is a racemic mixture. So we're going to have two different products. We're going to have a product that looks like this, which would give us the R configuration at this stereocenter. Plus, we would have the S configuration, so it's enantiomer. Again, both of these products would be a racemic mixture, not allowing us to see the optical activity of this solution. So it is important to mention that a chiral component must be present for the reaction to be stereoselective. So 1 enantiomer in excess. So if a reaction begins without chirality, it also must end without chirality. So in this case here, we have the production of a racemic mixture. So another thing that chemists can do to kind of target what they want is they can use a chiral catalyst. So this is going to be considered stereoselective, which means, again, one of the enantiomers would be in excess. So if we have something that looks like this, we react it with, again, hydrogen. So what we can do here is you can kind of pick the catalyst that you want. So if we choose a chiral catalyst that is going to favor R, that means that our major product here would be the R configuration. So the S configuration may be present, but it would be either a very minor product or it would not be produced at all. So the chiral catalyst can favor either the R or S configuration depending on which catalyst that you choose to use. But again, this is a way to obtain a stereoselective product, which again means one of the enantiomers in excess. And the last reaction that we're going to look at today is going to be a reaction at an achiral center in a chiral molecule. So if we look at this molecule here, and we react it with hydrogen and a nickel catalyst, we're going to have two different products formed. So we're going to have something here plus we're going to have this product here. So this would be our major product. This would be our minor product. These are going to be considered diastereomers. So this stereocenter that was here is going to, the stereochemistry at this position is going to stay the same. The stereochemistry at this position here is what is changing. So this is going to complete chapter 5. So make sure that you're doing the drill problems, the homework sets, and then again, we will have a review session on April 8th, and you can ask any questions that you may have to prepare you the best for the quiz that will be due April 10th. Have a great day,